Hey everyone, on this lesson we are going to solve the problem 10 on the collection of problems about context-free grammars. So, this problem 10 says, write and give a non-ambiguous context-free grammar to generate all the words that belong to this language, and we can see that this language is basically all the words of the form a to the power of I, b to the power of j, c to the power of k, such that the number of a's is the same as the number of b's plus the number of c's, right? So we have to give this grammar to generate all the words of this language. In other words, the language recognized by the grammar, okay, needs to be the same as this language described above. So first of all, before building this grammar, we will first analyze this language, we will deeply understand this language, we will see some instances of words that belong to this language, then we will see some words that do not belong to this language, and then finally we will give this context-free grammar. So, this is our language, right? As we can see, we have two main things to take into account. The first thing is the format of the word, in the sense all the words that belong to this language, okay, they need to follow this format. We will need to first have the a's, the sequence of all the a's, a total of I number of a's. Remember that when we have a power in a terminal symbol, it means how many times this symbol is repeated, right, next to each other. So we have here a number I of a's, then we have here b1, for instance, b2. We can also have 0 b's, okay, until JBs, and finally we have C1, C2, until KCs, right? So we have here a total of IAs, a total of JBs, and a total of KCs. So let's first see some words that belong to this language, okay? This was first the main thing, and the other main thing is that we need to satisfy this condition, okay? That the number of A's needs to be exactly and precisely the sum of the number of b's plus the number of c's. So for instance, let's consider this word. Imagine if I have the word w, okay, which is the word a, b, c, right? This is a word that belongs to this language. It is an accepting word. Why? Well, if we count how many a's we have here, how many a's we have? We have 2 a's, right? How many b's we have? We have 1 b. And c's, so here let's just say that j is 1, we have only 1 c also, so k is also 1. Now, if we take this equation and this equality, we see that 2 is equal to 1 plus 1, and this is true, so we satisfy on one side the format, the idea of first having the a's, then having the b's, and then having the c's, and we also satisfy the equation, right? So this is an accepted word. On the same way, for instance, we can have the word a, and then we have b, c, c, c. Here, if we count how many a's we have, right, we see that we have a total of 5 a's, so here di is 5, right, as we can see. How many b's? Well, we have 2 b's. How many c's? We have a total of 3 c's. And as we can see, 5 is equal to 2 plus 3. So we have the format by one side satisfied, and we also satisfy the equation. So we conclude that this word belongs to the language, right? As we can see, it is pretty simple. Even, okay, and in addition, it's important to know here that the empty word, the lambda, remember that lambda is the empty word. If I have the word is equal to lambda, okay, let's consider the word lambda. This is the empty word. This word also belongs to the language because how many a's I have? I have 0 a's, I have 0 b's as well, and I have 0 c's too. And if we go to the equation, we have something like 0 is equal to 0 plus 0, which is also true. So the empty word also belongs to this language, right? And we need to be able to generate the empty word with this grammar. Very well, once we have seen the words that belong to this language, let's see some of them and some instances that do not belong to this language, right? So for instance, whatever we can think of that does not satisfy this format or does not satisfy this equation will not be an accepting word. For instance, let's start with the word A, B, B, C. If this is my word, we can already see very easy that this word does not belong to the language. Okay, it is not difficult to see that I have only two A's, I have only two B's, and now I have one C. Now what happens? If I go to the equation, okay, I is equal to j plus k, so I have 2 is equal to 2 plus 1. So, okay, j is the number of b's, k is the number of c's, and we have what? We have the 2 is equal to 3, and this is false. Okay, this is false, so then this does not belong to the language. This is one example of a word that does not belong to the language because of the equation, However, keep in mind that we can also have one example like this, or any word like this. For instance, imagine that W is the word A, B, B, A, okay, and I have C and C. Now, what happens if you analyze this word? Well, you can try to count how many A's you have, and how many B's and how many C, that is, the occurrences of the terminal symbols. So you will basically see that we have a total of 5 A's, so I is 4. We have a total of 2 B's, so J is 2. And we also have a total of 2 C's, right? So K is 2. So now if we go to the equation, we have something like 4 is equal to 2 plus 2. So we have 4 is equal to 4. This is true. However, what happens? Does this word belong to the language? Then the answer is no. Okay, is a strong no. Why? Because what we have here, we do not have the format satisfied. We do not have first the A's, then the B's, and then the C's. What do we have? Well, we have first the A's, then the B's, then the A again. And this is very important to know. We have another A. We cannot have something like this. And then we have the C's. So we do not follow this format, okay? And this is one condition to meet. So we conclude that this word, okay, does not belong to the language because of the format of this word, right? Even though the equation is satisfied, the format is not satisfied, right? Very well. Once we have seen the words that this language accepts and the words that this language does not accept, okay, and we deeply understand this language, let's start with the construction and the building of this context-free grammar. So we will begin, as always, starting from the initial state, right? This is the initial state. And now, to have the idea of having the condition of the statement met, this equation to meet, we need to ensure that I have that the number of A's in my word is exactly the sum of the number of B's and C's. Not more, not less, right? And this is we need to have precisely this same value. So what we need to ensure here is that we can divide this grammar, okay, to have this language generated into cases. In a sense of, if I have words like this, let's just consider a word that is an accepting word, okay, and you will understand this deeply. So imagine that I have this word. Let's just consider the word W is the word A. Let's just say that I have 4 A's, then I have 3 B's, okay, and then I have 1 C. So to make this even more interesting, let's just say that I have 5 A's, I have 2 B's, okay, and then I have 3 C's. So how can I generate this word? Okay, well, the idea is that we will have one state to generate the A's and the C's all together. And this idea of generating the A's and the C's in the same time is key, okay? This is very important to understand. When we say that we generate at the same time, what does this mean? Well, when I want to generate, for instance, this first A and this first C in the same time, I can just say something like this. I generate this A and this C, like so. Here I have the A, here I have the C, and all this, okay, in the middle, I call it again S. So my state S is going to be a state that I generate the first A and the last C. And then again, if I have another C, what do we do? we again generate the second A and the second C starting from the right, okay, and here starting from the left. So I have again this A and this C, and this is again I have the state S. So I keep doing this. Here I have the A and here I have the C, okay, and here again I have the state S, A and C. Now here what happens? Well, we do not have a C, we have a B. So now, since I have reached the B, we know for sure that we will not have more C's. Because if I have more C's, it means that the word will not be an accepting word. And I must not be able to generate this word if it's a non-accepting word, right? So if I have reached this case or this situation, then let's just put it on blue, for instance. I generate this A with this B, okay, in a sequential way, in the same time. But now instead of writing here S, we will go to another state. Let's just call it the state B. And in the same way here I have the state B, right? So let's define this grammar in this way. The main thing here, okay, and the most important idea to understand this grammar is that I will have two states, the state S and the state B. The state S, apart from being the initial state, is also the state that I generate the A's and the C's in the same time. And then on the state B, I generate the A's and the B's, right? So here let's just define this, and we will erase this now. So as we've said, the state S, okay, as we just explained, will generate the A, let's put it here. Then again I call the S and then the C, right? Like so. Or, okay, I just go to B. Remember that this is a production rule. This means that from S I can substitute S, okay, it is a substitution. From S I can derive and produce this A as C, or from S I can also substitute S to go to B. And then B, we can define it here below. Let's define B now. So the state B, as we've said, is to generate A's and B's. So here I have A, B, B, right? And now we also need to have a way to stop this generation process. Otherwise, we will have a infinite length word, right? A word of infinite size. So here, as we've explained before, since the empty word also belongs to this language, we can have here the empty word, right? Like so. So basically here, remember, you can write the empty word or you can just leave a blank, okay? If you write a vertical bar and leave a blank, this is equivalent to having here the empty word. Very well. First of all, let's write formally the grammar. So here we start from the state S, which is the initial state. From S, we can keep generating the A's and the C's, or we can just go to B, and to B, we can just generate the A's and the B's, or we can have only the empty word. So this is important to also notice that you can have something like this. Just consider this word, the word W to be A, B, B, B. Now, what is up with this word? This word basically from S, the first production rule is this one. You will not generate neither A, neither C in here. We will just go from S to B. Yes, understood? And we just, once we are in B, we just make these productions, right? And in the same way, we can have something like this, A, C, C. Okay, this is a word that the first production is generating this 2 times, and then we substitute S to go to B, and once we are in B, we just go to the empty word, which is the blank. That's why we don't have any B's in this word. So just consider a word like this. Imagine that the word W is the one that we want to generate, and this is a word that belongs to the language. It is the word A, B, C. This is an accepting word, right? This is an accepted word. Why? Well, because it satisfies the condition, the format, and also the equation. So how can I generate this word with this grammar? Well, let's do this. From S, what do? Let's do it step by step. The first thing is, from the initial state, we need to see, do we have any A's and C's, or basically, do we have any C in this word? Yes, we do. We have this C. So the first production is to generate A, S, C, right? So from S, we generate this. And once we are in here, we already generate this A and this C. We only need to generate an A and a B. So from S, we substitute S to be B. So we have something like this. A, B, C. So I just substitute from S, I go to B. So I have this B. And then what do we do? Well, we just generate the A and the B with this production. So I have A that I had before. Then I substitute B with this. Okay. And this is a B. Okay. Important. This is not a C, right? This is a B. So I have here A, B, C, and then I have the C that I have before. Well, this is B, like so, and then I have the C, right? So once we are here, we just substitute dB to be the empty word. So I have A lambda, B, C, and when we concatenate lambda with any word, we have the same word. So A, B, C, right? So we have here this generation. So you can already check that for any word that belongs to the language, you will be able to generate this word with this grammar, right? For instance, consider here the word that you may have. Let's just say, let's check the word, for instance, A, B, C, C, C. So this is also an accepted word. So we just have here the productions to do. The first production is this one. Then from S, we again do the same. We do the same until we have here the final word, okay? It is very easy to understand. We just keep applying the production rules. You can have something like this. We have a total of 7 A's. So I have 1, 2, 3, 4, 1, 2, 3. Okay, this is also a valid word. The word AC is also a valid word, like so. AB also. But if you have something like this, AAB, this is a non-valid, so we cannot generate this word. And in the same way, if you have something like this, it won't be generated. Okay, we only generate the words that belong to this language. So with this, we finish the solution to this problem 10. We remind the student that you can check the solution to this problem, as well as the problem statement, on the downloadable documents of this lesson. See you in the next lesson.